So next, we're going to be talking about angled projectiles. So angled projectiles are kind of interesting. We have some object, right, that's launched at some angle with some velocity. And more often than not, we're asked how far does it go? For these problems that I'm going to be doing specifically, we're assuming that the vertical displacement or a change in y is 0, so that such that the object, it goes up and it comes back down to the same vertical height in which it landed. So I have a problem set up. Projectiles fired at 20 meters per second at an angle of 30 degrees above the horizontal. How far does it go? So there's a slow way to figure this problem out. There's also another way that we can derive. And so what I was going to do is go through that derivation and show you a equation that you can use anytime a projectile is launched at a level horizontal plane. So we have these up here. What we're going to start off with is simply this. If we're solving for horizontal range, we're looking for, or we're using this equation, that means eventually. If we solve for a horizontal range, we get change in x is equal to our horizontal displacement multiplied, or sorry, horizontal velocity multiplied by our time. If we were to look at a horizontal velocity, it's down here. If you guys know any trig, the way we would solve for your horizontal velocity would really just be v in the x direction is equal to your cosine theta multiplied by your just velocity, your the velocity that the ball gets launched up, not the horizontal or the vertical, but just the normal velocity. So we would kind of reduce that to v cosine theta. And this, if you know, for example, if you've ever heard of SOHCAHTOA, then you know why this is. But if you have not heard of that, don't worry. I'm just going through a derivation. If you don't understand the derivation, it doesn't matter. Just you can use the equation at the end of this derivation. But I wanted to show you where it comes from. So our Vx down here is really equal to v cosine theta, where v is, of course, 20 meters per second. Something that we haven't used, I haven't talked about yet, your v initial in the y direction. I'm just going to do that really quick too as well. That's just going to equal v sine theta. And again, if you know the SOHCAHTOA rules, that is where that would come from. So these two will be very important. So our Vx, I'm sorry, I wrote this line down here, but I haven't been using that consistently in the last videos, is actually just then v cosine theta multiplied by t. And what we have to do now is figure out what this t is. And if we remember, t is completely and solely dependent on how long this thing is in the air for. Well, we have done another problem before where a ball goes straight up and then it comes straight back down. That's kind of the vertical problem we're going to be solving for. So if we look at a type problem like that, we have change in y is equal to vit in the y direction plus 1/2 at squared, all again in the y direction. So what we can do then is assume that our vertical displacement is 0. So we'll have 0 equals, and let's remember that VIY, right, is just equal to v sine theta. So I'll put v sine theta multiplied by t plus 1/2, and let's remember its gravity is the acceleration for objects in free fall, t squared. Now what I can do is divide this whole thing by t. What that does is that cancels out some of the t's, and that gets us v0 equals v sine theta plus 1/2 g multiplied by t. Now, right, I've been looking for t the whole time. I can solve for t on this side. Well, t just equals then, and this is just, I'm doing algebra really quickly. It's just 2v sine theta, oops, over g. That is equal to our time. So now what we can do is we can plug this into here. So if we do that, we get a change in x is equal to v cosine theta. Then we just plug this in. We have 2v sine theta. Let me erase some of this kind of in the way. 2v sine theta over g. Now I'm just going to use algebra to, again, reduce this. If If I have two v's, that becomes v squared. I can move this 2 to the outside of the equation. So I'll have 2v squared. And then I'm going to have this whole equation divided by g. And then what we're left with is sine theta and cosine theta. You guys will not know it. And actually, I guess I should have left this 2 on the outside. So I'm actually going to have it here. There's a trig function where 2 sine theta cosine theta is actually just equal to sine 2 theta. So sine multiplied, or sine of 2 times the angle that you have. So what we can then say is that this part reduces down to just sine 2 theta. And we can say change in x then, which is our range, is just v squared, which is the velocity that the projectile is launched at, divided by your gravity, multiplied then by sine of 2 times your angle, right? So this equation right here, this is to solve for range of a projectile launched on a horizontal plane. So we go back to the problem, right? We have projectiles fired at 20 meters per second, so we can start plugging those things in. So we have 20 squared over gravity, which is just 10, multiplied by the sine of 2 times our angle is 30 degrees, right there. And so definitely try plugging this into your calculator. I'm going to plug that into my calculator currently, so it's going to take me a moment. So feel free to get yours out and try it now as well. So I got 34.6 meters. So there we go. That is all I'm really going to go over. Something else that you can think about is this. So if you have this problem, you have change in x, or sorry, this equation, and you have a horizontally launched projectile, then that means you can solve for a variety of things, right? If I give you your range, well, you already know what gravity is, right? It's just 10 meters per second squared. Well, if I give you those two things and I give you the angle, then that means you can also solve for the velocity that you were launched at. If I gave you the velocity you're launched at and the angle, that means you can find the range. And then if I gave you, which is what we just did, the range and the velocity, well, then you can eventually solve for the angle. But that will probably be a little bit harder because you might not know how an inverse sine works. So at the very least, though, if I give you range and I give you the angle, you can still solve for the velocity. So now, something else that you may be asked for is the thing that I just briefly skipped over, solving for those components of your velocity. So what I wanted to go through just really briefly is how you would do that. I believe you have technically done that before, but here's some basic rules. So if you have a right triangle, they follow some rules. So we had a velocity of 20 meters per second. And then we had some of these components, right? We also had an angle, theta, which is 30 degrees. So the nice thing about right triangles, the right part comes in right there, is that they follow some rules that are kind of easy for us to figure out. One rule is sine theta equals the length of the opposite side over the length of the hypotenuse. And it's okay that if our lengths are actually like velocities, as long as they're vectors, they should work. Hypotenuse, I'm not gonna spell it. I'm like blanking out on it right now. The cosine of your angle is equal to your adjacent side. I'm gonna do that over your hypotenuse. And then finally, your tangent of your angle is equal to the opposite side over the adjacent side. So if I'm solving for the components, I actually don't need tangent too much. I'm gonna be using these two, right? So now I'm gonna turn these equations into ones that are specific for our problem. So what we're really trying to figure out is, I'm gonna give these names. So we have the initial velocity in the y direction and the horizontal velocity. And sorry that I keep making that little line. That actually just means average. So there's nothing really to worry about with that. So I have these three. And then also, we'll call this just the velocity. So if we're looking for the horizontal portion, well, let's just look at sine. So if we have sine theta, that's going to equal our opposite side. Our opposite side is called VIY. And our hypotenuse is called V. Now, if we solve for VIY, we just have to multiply both sides by V. And we're left with V sine theta equals VIY, which is our initial velocity in the vertical direction. So that's where that came from. All I would need to do is take 20 times the sine of 30. Sine of 30, I believe, is 1/2. So you should get 10. Someone's actually easy. 20 sine of 30 degrees is equal to 10. Make sure you are in degree mode on your calculator. If you're on radians, you will get this wrong. You will get like a really, really small decimal. So yeah, just be aware of that. Now, if we have cosine theta, that is our adjacent side, which is our Vx, over our hypotenuse, which is V again. To get V onto the other side, multiply both sides by V. And so we get V cosine theta equals Vx. So now if I plug that in, we have 20, the cosine of 30 degrees. Cosine of 30 degrees is like 2 root 2 over 3 or something. I forget what the trig identity is. So I'm just going to put that into my calculator. We have the cosine of 30 times 20. We get 17.3 meters per second. Sorry, this one should have been meters per second. So if we were to look at these, right? If we look at our angle, it makes sense that our Vx should be larger than our Vy. And if we look at what we got, that is in fact what we got. So just to give them little vector notations, the 10 meters per second is the upward initial velocity, and the 17.3 is the horizontal constant velocity. And so that's how you solve that part. So that is all I have for you guys today. Please be careful though. For example, my vector that I have drawn this way, I could have just as easily drawn it this way. If I drew it that way, that's actually still okay. The only issue is though, is now this angle is 60 degrees and my vertical has switched with my horizontal. So now the horizontal is the opposite side and the vertical is the adjacent side. So be careful with that. If you just always draw them, however, where your horizontal is resting on your horizontal velocity is resting on your horizontal plane, you can pretty much use V sine theta is your initial velocity and V cosine theta is your Vx. So just to write them all out, we started with your velocity is equal to your range, change in x, is equal to V squared over G sine of 2 theta. And then we also had your horizontal velocity of a launched projectile is V cosine theta. And then your your vertical component of that same launched projectile is V sine theta. So here are your guys that will help you on the worksheet that you will have to do. So make sure you get that done. The solutions will be posted after the due date, right after the due date. So make sure you get that in.